Take a look at this graph. At first glance, it appears perfectly symmetrical around the y-axis. But watch what happens when we test this assumption. When we fold this graph over the y-axis, something interesting happens. The two sides don't match perfectly. There's a subtle but important difference. This raises a fascinating question that's crucial for success in calculus and advanced mathematics. What makes a function perfectly symmetrical? Understanding this concept, called even functions, will simplify complex calculations and give you a major advantage in calculus. In this video, we'll discover the mathematical definition of even functions, explore why f of negative x equals f of x guarantees perfect y-axis symmetry, and work through examples that will make you an expert at recognizing and using even functions. An even function is a special type of function with a very specific mathematical property. A function f of x is called even if f of negative x equals f of x for all x values in the function's domain. In simpler terms, this means that when you plug in any number and then plug in its negative, you will always get the same result. This is the key property that defines an even function. Let's see this in action with a concrete example. We'll use the function f of x equals x squared to demonstrate this property. Here we have the function f of x equals x squared. Now let's test whether this function satisfies our even function condition. We'll test this by plugging in x equals 2 and x equals negative 2. First, let's calculate f of 2. F of 2 equals 2 squared, which equals 4. Now let's calculate f of negative 2. F of negative 2 equals negative 2 squared. Remember, when we square a negative number, we get a positive result. So negative 2 squared equals positive 4. Notice that f of 2 equals f of negative 2, and both equal 4. This confirms that our function satisfies the even function condition. This property of getting the same output for both positive and negative inputs is what makes x squared an even function. This special behavior also leads to a beautiful geometric property called symmetry, which we'll explore in the next section. Now that we understand what makes a function even, let's examine 4 classic examples. For each function, we'll prove algebraically that f of negative x equals f of x, and then visualize their symmetric graphs. Our first example is f of x equals x squared. This is perhaps the most familiar even function. To prove this is even, we substitute negative x for x and simplify. F of negative x equals negative x squared. When we square negative x, we get positive x squared, because negative times negative equals positive. Since f of negative x equals x squared and f of x also equals x squared, we have proven that f of negative x equals f of x. The graph of x squared is a parabola that opens upward, perfectly symmetric about the y-axis. Our second example is f of x equals x to the 4th power. This follows the same pattern as x squared. Again, we substitute negative x for x. F of negative x equals negative x to the 4th power. Since we're raising negative x to an even power, the result is positive. Negative x to the 4th equals x to the 4th. Therefore, f of negative x equals f of x, confirming this is an even function. The graph of x to the 4th is flatter near the origin than x squared, but still perfectly symmetric about the y-axis. Our third example is the absolute value function, f of x equals the absolute value of x. For the absolute value function, f of negative x equals the absolute value of negative x. The absolute value of negative x is the same as the absolute value of x, because absolute value always gives us the positive distance from 0. Since f of negative x equals the absolute value of x, and f of x also equals the absolute value of x, we have f of negative x equals f of x. The graph of the absolute value function forms a V shape with perfect symmetry about the y-axis. Our final example is the cosine function. F of x equals cosine of x. This is our first trigonometric even function. To verify this is even, we need f of negative x equals cosine of negative x. From trigonometry, we know that cosine is an even function, so cosine of negative x equals cosine of x. Therefore, f of negative x equals f of x, confirming that cosine is indeed an even function. The graph of cosine shows the characteristic wave pattern, perfectly symmetric about the y-axis, oscillating between -1 and +1. These 4 examples demonstrate the key patterns of even functions. Polynomial functions with only even powers, the absolute value function, and the cosine function all exhibit perfect symmetry about the y-axis. Now we'll work through our first guided example to prove whether a function is even. We have the function f of x equals x to the sixth power plus 3. The question we need to answer is this function even? To determine if this function is even, we need to check if f of negative x equals f of x. Remember, this is the fundamental test for even functions. If this equality holds true, then our function is even. Step 1. We substitute negative x for x in our original function. This means everywhere we see x, we replace it with negative x. So f of negative x equals negative x to the sixth power plus 3. Step 2. Now we need to simplify negative x to the sixth power. This is a crucial step. Since 6 is an even number, negative x to an even power equals positive x to that same power. So negative x to the sixth equals x to the sixth. Step 3. We can now rewrite f of negative x using our simplified exponent. Since negative x to the sixth equals x to the sixth, we get f of negative x equals x to the sixth plus 3. Step 4. Now we compare our results. We have f of negative x equals x to the sixth plus 3, and our original function f of x equals x to the sixth plus 3. These expressions are identical. Conclusion: since f of negative x equals f of x, we can definitively say that the function f of x equals x to the sixth power plus 3 is an even function. Notice two key features that made this work: the even exponent 6 and the constant term 3, which doesn't change when we substitute negative x. Now for our second example, we have a more complex function involving a fraction. We need to determine if f of x equals x squared divided by 1 plus x to the fourth power is an even function. To test if this function is even, we need to substitute negative x for x and see if we get the same function back. Remember, a function is even if f of negative x equals f of x. First, let's substitute negative x into our function. We replace every x with negative x. Now we need to simplify this expression. Let's start with the numerator. We have negative x squared. Since we're raising negative x to an even power, the negative sign disappears. Next, let's look at the denominator. We have 1 plus negative x to the fourth power. Again, since 4 is an even number, negative x to the fourth equals x to the fourth. Now we can write our simplified result. After substituting and simplifying, f of negative x equals x squared divided by 1 plus x to the fourth. Now let's compare this result with our original function. Notice that f of negative x is exactly the same as f of x. Since f of negative x equals f of x, we can conclude that this function is even. The key insight here is that even powers eliminate negative signs. Remember this important principle. When you raise a negative number to an even power, the result is always positive. This is why negative x squared equals x squared, and negative x to the fourth equals x to the fourth. Even powers always eliminate the negative sign, which is crucial for identifying even functions. Now for our third example, we'll examine a function that is not even. Consider the function f of x equals x cubed. The question is this function even? To determine if this function is even, we need to apply our test. We substitute negative x for x and see if we get the same function back. Step 1. We substitute negative x for x in our function. This gives us f of negative x equals negative x to the third power. Step 2. We need to simplify negative x to the third power. Here's a crucial insight. When we have an odd power like 3, the negative sign stays outside. So negative x cubed equals negative x cubed. Step 3. Now we compare our results. We have f of x equals x cubed and f of negative x equals negative x cubed. These are clearly not the same expression. Since f of negative x does not equal f of x, we can conclude that this function is not even. The presence of the negative sign breaks the symmetry requirement. Now let's look at the graph of f of x equals x cubed to visually confirm our algebraic result. Notice the characteristic S-shaped curve of the cubic function. Look at these 2 points. When x equals 2, y equals 8. But when x equals negative 2, y equals negative 8, not positive 8. This confirms the function is not symmetric about the y-axis. The key insight is that odd powers like x cubed change the sign when we substitute negative x. This breaks the y-axis symmetry required for even functions. Instead, cubic functions have rotational symmetry about the origin. In conclusion, f of x equals x cubed is not an even function because it fails the symmetry test. The odd power creates a function that has rotational symmetry about the origin rather than reflection symmetry about the y-axis. We've covered a lot of ground with even functions today. These mathematical objects are fundamental to understanding symmetry in mathematics and will serve as building blocks for more advanced topics. First, remember the key definition. A function is even if f of negative x equals f of x for all values in its domain. This simple equation captures the essence of even functions. This definition directly translates to y-axis symmetry. When you graph an even function, you can fold it along the y-axis, and both halves will match perfectly. We explored several common examples: x squared, x to the fourth power, absolute value of x, and cosine of x. These functions appear frequently in mathematics and demonstrate the even function property clearly. To test whether any function is even, follow these steps. Replace x with negative x, simplify the resulting expression, and check if it equals the original function. Understanding even functions is crucial for several reasons. They simplify many mathematical calculations, especially in calculus, where symmetry properties can reduce complex integrals and make problem-solving more efficient. If this video helped you understand even functions better, please give it a thumbs up and subscribe for more mathematics content. Your support helps me create more educational videos like this one. What should we explore next? I'm thinking about covering odd functions, which have a different type of symmetry, or perhaps function transformations and how they affect symmetry. Let me know in the comments what you'd like to see. Keep practicing with even functions, and remember that mathematics is all about recognizing patterns and connections. The symmetry we've explored today appears throughout mathematics and science. Until next time, keep learning and stay curious.